Question number 7, a small gift to you from Dimension, and we got to calculate the dimensional formula for thermal conductivity. So let's find out the relationship about thermal conductivity. You can go with the basic one, the rate of heat transfer. That comes out to be Ka. K is the thermal conductivity, that's how we denote. But here in terms of dimension, K is also the dimension. So not to confuse with the variable, let me just write Kt. So that's the thermal conductivity, and K is going to be Kelvin. Ka d theta divided by dx. Now let's see, this is basically power, and power is ml square t minus 3, and kt will remain same. Area is L square. D theta, that's a temperature. So temperature will have a dimension K in Kelvin. Dx is length, so that's going to be L. So that's a straightforward one. That will be ml T minus 3 K minus 1. Here you have option number 2. Let's go for the 8th question. And here is this. Nicely framed from polarization. Now what does it say? There is a beam of plane polarized light. Notice the incident is plane polarized, and it has a large cross section, and it has an intensity this much. So what I'll do is that, let's say the intensity I is the intensity of that plane polarized beam. It falls normally on a polarizer of cross section area A that has been given. And this is rotating the polarizer with an angular velocity that's given as omega. We need to find the energy of the light that passes through the polarizer per revolution, in one revolution. You know, just to give you a nice view of what is happening there, I'll just take the help of a figure, and here let me make a polarizer first, okay? So this is the polarizer. And together, let me also make the way how energy would be passed. So this is the plane of polarization. That's how it goes. Now here, light is incident. So let's say the light is incident in this manner. And you know, the Malus law says that depending upon the angle between the plane of polarization of incident light and this, you would have various intensity transmitted. To give you a better view of that, it's something like this. If I say the incident beam is going in this direction, and right now this is the plane of polarization. So let's show with the help of figure. Cross is the direction of light, and this is theta. So how much will be the transmitted intensity, IT? That's going to be I cos square theta. And since the polarizer is rotating, so at various instances, the value of theta changes, and therefore the intensity changes. But we got to calculate the average energy that passes, right, in one revolution. So that's what we need to do. And we need to calculate the energy that passes in one revolution. Now, look at the question. It says is very close to. So we kind of make a sense intuitively. Instead of going through the integration process, let's directly go with the average computation. So here if you see, the average value of transmitted intensity will be equals to I by 2, because the average of cos square theta, that's 1 by 2. Otherwise, you need to go at a small instant, integrate, that's how you have to move. Now, what is intensity? Power per unit area. So, if that's the case, what will be the energy? Energy will be power, and for the power, we require I by 2 multiplied by A, that's the power, multiplied by time. Now, time for one revolution, so that's going to be 2 pi by omega. That's all. The power transmitted multiplied by the time during which the experiment is conducted. You do that calculation and you would get option number 2 as the correct one. Let's go for the next. The next is from electromagnetic induction and related to Lenz's law and very straightforward. It's something like this. There is a long coil and a magnet passes completely through the coil and comes out to the other end. During this process, we need to see how would the deflection of galvanometer orient itself. Remember, the coil is long because the bar magnet has been taken as small. So there would be three phases. One is the incoming, other is the outgoing, and other is the well inside. Now in well inside, the flux linkage is constant, therefore the EMF would be 0. While during incoming and outgoing, the direction has to change. So these are the clue points we have. And let's try to figure out the option. Like the first option says there's no deflection at all. So that is inconsistent. And if you just see, the fourth option is clearly visible. Because what does fourth option say? Initially there's one direction. And then when it is well inside, there's no deflection because the flux linkage is constant, and then the direction reverses. So for this, option number 4 is going to be the correct one. Let's go to the next.